From the car you drive to the phone in your hand, we are surrounded by these incredibly complex products. But have you ever stopped to wonder how they go from just a simple idea to a reliable, real-world object that you can actually hold and use? Well, today we're going to pull back the curtain on the invisible force that really makes all of modern engineering possible.
Just think about that for a second. Physical building and then crashing a car is unbelievably expensive, and it takes a ton of time. Trying to do it 1,000 times to test every single little design change, that would be completely impossible. So, how do engineers do it? This question right here gets to the absolute heart of a revolutionary shift in how we design and build our world.
For centuries, engineering followed a pretty simple and honestly kind of brutal logic. You build it, you break it, and you hope you learn something from the pieces. It was a slow, expensive, and often pretty risky process. But now, what's so fascinating is how that's been completely flipped on its head. This move from a break-it-to-make-it philosophy to a simulate-first approach has totally revolutionized engineering.
So this new way we're talking about, it's all powered by something called computational simulation. You can think of it as a virtual test lab that exists entirely on a computer, and it lets us see the future of a product without ever having to build it in the first place.
I love this definition. It just nails it. A digital dress rehearsal for reality. It's basically like having a crystal ball for your product. You get to ask all those critical questions beforehand. Will it bend under pressure? Is it going to overheat in extreme conditions? Will it be as efficient as you hope? Well, simulation gives us the answers before we've even built a single physical prototype.
So how does this digital rehearsal actually play out? Well, it all starts with a digital blueprint, usually what's called a CAD model. Then, engineers start applying virtual conditions. The crushing force of a car crash, the air pressure on an airplane's wing, the intense heat inside an engine. And finally, the computer becomes this virtual lab, crunching all the numbers to show you exactly where the stress points are, predict how fluids will flow, or even estimate the lifespan of a part.
Okay, so simulation isn't just one magic button you press. It's really more like a toolbox, with different specialized tools for different jobs. Let's take a quick look at a few of the most important ones.
First up is one of the real heavy hitters, finite element analysis, or you'll just hear it called FEA. This is the absolute go-to tool for understanding how a solid object is going to behave under stress. Think of it as a virtual stress test for, everything from a tiny bracket to an entire airplane wing.
This quote just explains the whole idea perfectly. The software digitally carves up a really complex object into thousands, sometimes millions, of simple little finite elements, kind of like digital Legos. By calculating the forces on every single one of those little pieces, it builds an incredibly accurate picture of how the entire object is going to react when it's pushed, pulled, or twisted. So if FEA is for solids, what about liquids and gases? For that, we turn to our next tool, Computational Fluid Dynamics, or CFD.
This is such a great way to think about it. Seriously, imagine being able to see the invisible currents of air flowing over a car to perfect its aerodynamics. Or picture visualizing the complex dance of water rushing through a turbine so you can squeeze out every last bit of efficiency. That's the power of CFD.
Okay, so we've covered solids and we've covered fluids. But what about when you have a whole bunch of parts all moving together in a really complex system? For that, engineers turn to something called multi-body dynamics.
The key takeaway here is that this isn't just about one part, it's about the whole shebang. The source material gives this fantastic example of building a virtual prototype of a milling machine, just to simulate how all its components interact, analyzing vibrations and performance way before it's ever assembled. It's like building and running the entire machine before a single screw gets turned.
All right, theory is great, but where does the rubber meet the road? This is where it gets really, really exciting. Let's look at some real-world examples of simulation in action.
We started with cars, so let's go right back there. Simulation is used for pretty much everything, from analyzing the twisting force on a clutch to predicting how long gears and tires are going to last under stress. Every single component is tested and optimized in this virtual world to make the car you drive safer and more reliable.
It's also happening behind the scenes, in places you'd never expect. In manufacturing, engineers simulate how molten metal flows into a die to create a part. By analyzing the stress and spotting potential defects digitally, they can perfect the die's design and prevent these really expensive failures on the factory floor.
And then you get to aerospace, where the stakes are, literally sky high.
Here, engineers use finite element analysis to validate the structural reliability of critical components like the arm of a drone or a UAV, making absolutely sure it can withstand all the stresses it's going to face in flight.
And this one might surprise you. Simulation is actually revolutionizing medicine. By creating these incredibly detailed 3D models of a patient's femur and cartilage, doctors and engineers can simulate how different knee replacement designs will perform. It's just a perfect example of how simulation isn't just changing how we build machines, but also how we heal our bodies.
So, we've seen what simulation is and what it can do. But what does this all really mean for the future? Where's this technology headed next?
The next great leap forward is this concept called the digital twin. Now, this isn't just a pre-production model, it's a living, breathing, digital doppelganger that stays connected to its physical counterpart through its entire life, constantly being updated with data from real-world sensors.
Now, what's really interesting here is the distinction. A standard simulation is kind of like a snapshot. It's a prediction made at the design stage. But a digital twin, oh, that's like a full-length feature film. It mirrors the physical object in real time. This lets operators monitor its health, predict failures before they ever happen, and even test out future scenarios on the virtual copy without ever risking the real thing.
And look, none of this would matter if it wasn't accurate. But it is. It's astonishingly accurate. The source material points out that in some cases, the error rate between what the simulation predicts and what happens in the real world is less than 7%. I mean, that is an incredible level of accuracy. And it's why entire industries are betting the farm on these digital models.
So, what's the ultimate payoff? When you boil it all down, it's this. Simulation lets us innovate faster because we can test countless ideas digitally. It dramatically lowers costs by cutting down on physical prototypes. It increases safety by catching flaws early on. And maybe most importantly, it makes it possible to design and build things that were just too complex to even try with the old build and break method.
This technology has fundamentally changed how we create our physical world. It's given us the power to see the future of our own inventions. Which leaves us with a final, really fascinating question to think about. If our ability to build a digital dress rehearsal for reality is becoming this powerful, what challenges that once seemed impossible should we start simulating now?